to tell you the story of the Red Sea, of the Gulf of Aqaba, where we are. Perhaps would be the right thing to do in this community, so that you would appreciate the difference between the Great Barrier Reef here, not only in size and the Gulf of Aqaba, but in the functioning, the way this Gulf is functioning, which in my opinion has no parallel in the world, and that's what I would like to convey today. So the focus of the talk will be on, it will consist of two chapters. One is why we don't get bleaching in Eilat, and this photograph is of course from here, from the GPR, and why sometimes we get the reef covered with algae, with a thick layer of algae that smothers coral. So we have mortality due to the algae, but we don't have mortality due to bleaching, and it all is related to one parameter that I would try to convince you that that's the case. So before I start, I have to acknowledge Maoz Fine, that I'm sure many of you know. He's a co-author on the lack of bleaching, the lead author on that paper, and Chezi Gildor, a physical oceanographer. And in the second chapter, I would like to acknowledge the monitoring. We have a national monitoring program at our institute that monitors both the coral reef and the open oceans, and much of our understanding comes from this monitoring. That, by the way, it's open public domain, so anybody who wants to know what's going on there, I can guide you on how to access the data. And a little bit background on where we are, although there is some light here that doesn't provide the details, but here, that's our institute. That's the IOI, the Inter-University Institute, that belongs to all the institutes or universities in Israel. That's the way it looks like from the air, and we are right on the water, and the coral reef that you can see here comes all the way here, and it's very accessible. We don't have waves, we don't have sharks, so you can work 24 hours a day and go into the water, and we can use the pier here and also places here to extend cables and monitor in real time many parameters, and also using the power source at the lab and on the pier to manipulate things. So you can grow corals under whatever current regime you want by putting some pumps that will pump water and increase the speed, or nutrients, or whatever you want. And we take major advantage of that. Some of this will be reflected here. Where we are. So here's the Indian Ocean. So in order to get to Eilat, you have to go through the Gulf of Eden here, and then 2,000 kilometers Red Sea, and then here's the Gulf of Aqaba, 180 kilometers, and we are right here at the tip. And since that area is tectonically active, so that plate is getting away from the plate here of Africa. So this is an ocean in the opening, and therefore we have a very steep slope. It's active, and it's actively being open. So in a boat ride of about, 5 minutes, you get to bottom depth of 750 meters. So that's pretty deep water body. And if you go beyond the border, so the border with Egypt is right here. If you go further to the south, you get to 900 meters, and the deepest place in the Gulf is over about 2 kilometers in depth. And if we go to the Red Sea further down, then you get to almost 2.5 kilometers in depth. And I'd like to provide some background to the oceanography of this water body. We have about 0.5 centimeter evaporation every day. It's very dry. We don't have any input of fresh water. Even, the big river that drains all that area in Africa, the Nile, it goes to the Mediterranean. It doesn't go to the Red Sea. So there is not much of input here. Evaporation of 0.5 centimeter a day over 2,000 kilometers. You need to get water back into the Gulf, into the Red Sea, and all the water comes from here, from the Straits, except that the Strait is it's called Bab el Mandeb. The place is very shallow, 137 meters in depth. Now that has lots of implications, as we will see later on. The circulation above the sill here is that we get flow in the upper layer, so the upper 80 meters or so, and outflow of denser water that makes creates the bottom water here in the Gulf of Aden that goes above the sill. Sometimes in some season you have also influx of water at depth, but most of the water comes at the shallow, layer of about 80 meters, as I said, and that compensates for the salinity or the loss of fresh water. So overall, this is the highest salinity in any ocean that is connected to the open ocean, or any sea that is connected. We get salinity by the time the water gets to Eilat. We have about 41 per mil salinity, which is really high. Then we get, alerts, extreme alerts. It's hard to see the colors there, but we are really in the dark blue, red area of the bleaching alert, and yet we don't get bleaching. There has never been bleaching in the Gulf of Aqaba. There is bleaching in the Red Sea, but not in the Gulf of Aqaba. To the best we know, records didn't start too long ago, but we don't get bleaching, and yet the water is warming. So this is from the monitoring program. For 30 years, we are measuring the temperature, the sea surface temperature, and the rate of warming is more or less the average, 3-point-something degrees per 100 years. And the water now is warmer than when we started, of course. And if you calculate the bleaching, the temperature, the heating weeks, and to what extent we should have seen bleaching in the Gulf, then there were several years that bleaching should have occurred if the corals follow the 1.5 rule of warming and then following the loss of zooxanthellae. Yet the corals don't bleach in Eilat. And we ask ourselves, how come? But before that, we did some experiments. This is Maoz's part. So Maoz warmed up the corals. He has a simulator similar in essence, but not in magnitude and beauty, as I saw yesterday at Ames. But it's functional and it works very well. And he took corals, several species, from the coral reef in Eilat, so Stylophora, Procylopora, and others, and he incubated them in his simulator. He gradually warmed up the water, and it got 7 degrees above the local maximum. And bleaching signs, none. The group of Christine Ferrier from Monaco, they come and they study warming effect and bleaching in the corals. They come and they collect the Stylophora and other corals in Aqaba and also in Eilat, and they warm up. They boil the corals, and the corals eventually die by perhaps denaturalization of proteins. The proteins get knocked down, but zooxanthellae no. They never bleach. So what's going on here? If we go back 20,000 years, and that graph is taken from a paper by Sidol, then during the peak of the glacial period, so 20,000 years ago, sea level was about 120 meters below present, all over the oceans, and including the Red Sea. These papers coming from the Red Sea, and they reconstructed the sea level. And if you look at the sea level at present in black and in blue, the peak of the glacial, then all is left here. If you take 120 meters below, all is left here is 17 meters of water. Evaporation, cold air, and if the water was warm, of course less warm than today, but cold air is a very effective means of getting evaporation high, and I'll get to that later. So if you have only 17 meters here, at 17 meters of passage. You cannot have this steady state balance between the influx of relatively fresher water and the outflux of saltier water to keep the balance, and salinity would definitely go up. And here from the same paper by Sidal, they modeled the salinity there. You cannot find any fauna to analyze in foraminifera, the stable isotopes, because as they call it here, the gray areas, they call it aplanktonic period. Why? Because based on simulations that are based on the period that there were some animals or that there are fossils from that period, they modeled the salinity and they predicted something like on the order of maybe 65 per mil of standard units of salinity. The only organisms left there were bacteria, halophilic bacteria. No coral reef, no fish, no foraminifera. All the metazoans are just gone. There is no fossil record from the glacial periods, and that's not the only one, but there was another one. So we have a reset of the coral reef of Eilat, not of the Red Sea, including the Gulf of Aqaba. So eradication of a coral reef inside the Red Sea, but outside we still have coral reefs. So if we go back in time to 8,000 years ago, sea level again was high, closer to the present. Conditions were already ripe for corals to start going into the Gulf again, and recolonization of corals into the Red Sea could have originated only in the Indian Ocean. Now let's simulate, and that's what we did with Chezi Gildo, the physical oceanographer. Let's simulate the influx of larvae of coral planulae into the Red Sea from this area here. And if you get planulae, most of the corals would have short-lived planulae, right? So they would be in the water on the order of days. Let's take those species that perhaps have the larvae out there in the plankton, in the planktonic stage, and still capable of recruiting for 1 month. So how far into the Red Sea they would get into 1 month, and Chezi modeled that, and still the larvae would stay within, this is the results of the model, they would stay in this warm area here, which has about 32 degrees in the summer. Now, in order so the way the corals would get, eventually they would get to Eilat, and the line is more or less, south to north or higher latitude here, is that they would get here and then another stepping stone. So the maximum stepping stone here would retain them in the warm area, and then the corals would settle. And how long would it take them to produce the next stepping stone, the larvae for the next stepping stone? At least 1 year, because the coral has to grow, start reproducing. So the fact is that they have to spend a summer in this area. So they have to sustain 32 degrees, maybe 34. So this is a very effective selective barrier, perhaps similar to what Van Open is doing it there, and in the simulator and Ruth Gates in Hawaii. She used to do that because you select only those individuals or colonies that can survive high temperature. Those corals that cannot sustain in the holobiont of the coral and the Zooxanthellae, those that cannot sustain 34 degrees, 32, 34 degrees, would not enter the Red Sea, would not survive in the Red Sea. And eventually, they made it all the way here to Eilat, and Eilat is 29.5 degrees north. Maximum temperature in Eilat is 27, 28 degrees. These corals are adapted to 32. And therefore, if we take the maximum 28, we warm up the water to 29.5 for the 1.5 degrees rule, they would not bleach because they went through this selectivity of very warm waters. So we think that we claim that that's the explanation for the lack of bleaching. Without bleaching, the reef in Eilat is doing pretty well. Unlike some really disturbing trends that we find from papers coming from here, from the GPR, in Eilat, the coral cover gradually increasing, very gradually, very slowly. But we got rid also of the fish cages that used to be in the long past in Eilat, so there are no major sources of eutrophication. Now also pollution is pretty well controlled. So we have an increase both in coral density and in coral coverage. So the reef, overall the reef is stable and is doing well. Diversity is stable from the days of Yossi Goya, like 50 years ago, has not changed much. So if we summarize what this chapter of the talk, so we find a refuge from bleaching in the Gulf of Aqaba. I must emphasize again, it's only the Gulf of Aqaba. It's not the Red Sea. The Red Sea is warm enough so they get warming that bleach the corals there, so they get bleaching event, but only from the central part, or not in the very northern part of the Red Sea, which is already sufficiently cold, or it doesn't get that warm in the northern parts. But Gulf of Aqaba is really an exception, I think, as far as the size of the site that doesn't get bleached. We claim we ask people, let's work and declare that a World Heritage Site, but that politics in the Middle East is so complex. So we have Jordan, Saudi Arabia, Israel, Egypt, and it didn't go anywhere. So far it's not World Heritage Site. But I think that it needs to have more emphasized by the community here, because think about what we can learn from there, and this is just a tip, I think. So it needs to be used. For example, we have 8,000. The age of the corals, the modern coral reef in Eilat is 8,000 years. These corals are adapted to the temperature of 32, 34, but here they live for 8,000 years in waters that are much colder. Now, in evolutionary terms, did they lose the adaptation to bleaching? No, they didn't. So if we think about how long, what is the dynamics in evolutionary time of this adaptation, and what is the selective force to lose the genes that would allow that adaptation? So here you can use that in order to study things like that, and I think it's studying now, much due to Mo's find, and he finds some collaboration in the south, and so they look at that. But we are not in the initiative for the 50 reefs. The Red Sea is not part of it, or at least not the Gulf is not part of it, and I advocate that. So, based on our calculations, and they're publishing that bleaching will start on the current rate of bleaching, of warming, in Eilat. It will take another 100 years before we start seeing bleaching in the Gulf of Aqaba. And they're publishing that, and then there. I bought really small hat. I immersed it in good sauce, and because if bleaching occurs in Eilat, I'll have to eat my hat. So it's I don't know, but we did putting that prediction that bleaching would not occur there. Maoz is dubious. He said, well, if we keep the synergetic effect to the minimum here, like if there would be more pollution and more disturbance by tourism, and the corals would feel, maybe synergetic effect would have that. But that's what we think going on now, and let's move to the second chapter. What does kill corals in Eilat? And this is the massive algal bloom. And the roots are the same as I would lead you to right now. So that's the same plot that we had before of the inflow of water at the surface, near the surface, upper 80 meters, and outflow down below. So what does it mean that we get water definitely shallower than 130 meters? That's the depth of the sill here, but perhaps even shallower. If you look at a temperature profile in any ocean, you have stratification. So this is taken from a Y. The surface temperature is 27, and then if you go down to 137 meters here, then you get about 130. It would be something 21 degrees centigrade. But the deeper water, which is heavier and colder, would not go because of the sill depth. It's too shallow for cold, heavier water to come over the sill and enter the Red Sea. So therefore, in the Red Sea, there is no source of cold water. The coldest place in the Red Sea is Eilat. So Eilat in the winter, you'll see the temperature. I mean, we still wear shorts in Eilat in the winter time. Well, maybe sometimes we put long pants, but there is no really source of cold water in the Red Sea, and therefore, if you lower a CTD here, and now it's well known, if you lower a CTD here to 2.5 kilometers deep here in the center of the Red Sea, the temperature here at 2.5 kilometers deep, which usually I didn't get here, but it's usually around 2 to 3 degrees. In the Red Sea, 21 degrees. Really warm water in the Red Sea. That has implications to zooplankton and fluxes, because you have bacteria that work under 20 degrees through the water column, so much less organic material get to the bottom. And that's an opening for a whole world to compare the deep sea biology in the Red Sea to other places in the world, and it has been done and being done right now, but that's the difference. So we don't get cold water, and therefore stratification, the difference in the water buoyancy between the surface and the deep layers is very, very weak. We don't get strong stratification ever and ever in the Red Sea, but more so in Eilat. So if you compare the temperature, say the previous graph in Hawaii, which has similar sea surface temperature to what we find in Eilat. So in Eilat it goes down to 21 degrees at 700, that's in our monitoring station of the lab in Eilat. Here in Hawaii, you get 16 degrees difference between the surface and the deep water, whereas here you get only 6 degrees difference between here and there. So comes the winter, and still we get lower temperature during the winter, and I'll show you that graph. It's enough. The cooling in the winter is enough to push the surface to cool down this surface temperature to that temperature. So if you create convective mixing by the cooling here, every year we get convective mixing that reaches this depth, and if it's colder, it may reach even this depth. And if it reaches this depth, it's enough that you extend the winter by maybe 2 weeks, or you lower the air temperature by 1/10 of a degree. Then to deepen the mixing from here to here doesn't take much, because you only have to cool by a few hundredths of a degrees the water in order to get the mixing. If the mixing reaches here, to cool it down, and then you extend the mixing depth by 200 meters depending on the length of the winter, how cold it got during that winter. So in cold winters we get deep mixing. Now it never happens, and I will skip that slide, it never happens in Hawaii, because in Hawaii, they have Antarctica and Greenland. In the general ocean you have these sources of really cold water, and therefore you get that strong stratification. And here's the temperature in Eilat. So in the winter time, the air temperature and the sea temperature. So air temperature during the winter, so starting in November and going all the way to the end of March, so April, depending on the year, there is interannual variability, but you get air temperature colder than the water temperature. Now that's the best means, the best tool to cool down the water for the biologists among us, that not all of us are really aware of that. The evaporation is the main process to cool down the surface, and I have, well, we cannot see it here with this light, but it's amazing to see that, like during the winter time, when you have days that the air temperature is about, here it was 15.5 degrees difference. The air was below 10 degrees, like 8 degrees, and the water was around 20 degrees, 21 degrees, and then you could actually see the water, being pumped into the air. Where is it? It's hard to see here because the water comes very dry from the desert around us, and the air comes very dry with the northerly wind. The wind always goes along the Gulf, and then it warms up as it evaporates the water, and then it shoots up to the atmosphere because it warms up, and dry air that doesn't have any water vapor in it comes down, and then you have this evaporation pump working very, very effectively. So the colder the winter, the more evaporation you get, and the colder the water, and then the deeper the mixing, the convective mixing during the winter. So here's just example from quite warm years. So 2005, you have the stratified water column in the summertime. Then you have November. The mixing got to 200 during this year. January it got there. In March, well, maybe down to 400 meters. But look, at March you already capped the mixing. In March the sun warms up the surface layer, no more mixing. Although you can call the deeper layer mixed layer, but what is unique about that the mixing is really mixed. I'll show you in a moment. And this is the mixing depth evaluated visually as I did before, and in warm years, what we get 200 and 300 meters. Maybe in really warm winter, we get less than 200 meters, but in cold years, you get about 700 meters. Like there is no ocean that I know of in the world that gets mixing down to 800 meters, 700 meters in cold. It simply never happens. We have Mediterranean, with the shallow Strait of Gibraltar, and they get, in very, very cold winters, they get mixing down to 300, 400 meters, maybe 400, but never to 800 meters. So this is a unique feature of the Gulf, and the mixed layer is it's not only homogeneous temperature that goes down. So this is the summer. And that's the winter, and here you can see the mixed layer at 21.1. But I want to point out the phytoplankton. So here is the chlorophyll fluorescence, and you get phytoplankton down to 600, 700, depending on the mixing layer. It gets down to precisely the depth of the mixed layer depth. And these phytoplanktons, the mixing is so intense, maybe you should. We don't have a physical oceanography that has modeled the residence time of the water. Like, how long, what is the expectancy of a cell, of a phytoplankton cell that now is found at 500 meters under complete darkness? Recall that the photic layer is about 100 meters, 120 meters. So those cells that are found here are in darkness. What is the expectancy of time? How long will it take them to come back to the light, to the shallow layers? We think it's on the order of a day or less than a day, because you don't see any gradient in chlorophyll, you don't see any gradient in oxygen, and oxygen, regardless of mixing, is produced by phytoplankton only in the deep water. In the layer. So oxygen is produced only in the upper layer by photosynthesis and exchange with the atmosphere, and yet the line looks straight. So the mixing must be very, very intensive. I would just mention on the side that you take water from 600 meters here during the mixing, and you take water from 20 meters, and you bring the water to the lab, and you illuminate both bottles, and the photosynthesis rate would be the same. Like the phytoplankton that is found down here is fully viable. It's respiring, it's viable. It has a lot to do with those of you who know the critical depth hypothesis of Sverdrup. So we work on that as well there. It doesn't work. I mean, there is no critical depth here. But we published that 2 years ago. Anyway, but it's a great place to study the adaptation of phytoplankton. But that's a side. We are still with corals. What I want to mention is that if you get deep mixing, the nutrient profile in the Gulf looks pretty normal, like you would find in any other ocean. In other words, nutrients are increasing with that. So if you get lots of, very deep mixing, then you get lots of nutrients in the surface layer. And that's the explanation for the bloom, of course. And because we have deep mixing every day, every year, every winter, the sea in Eilat, this is the chlorophyll dynamics, this is the bloom, 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 bloom. And I put here in red the chlorophyll in Bermuda, compared to another oligotrophic ocean. And you can see that the Gulf of Eilat or Gulf of Aqaba is not really extremely oligotrophic because of that mixing. So we get, and that affects the chlorophyll or the phytoplankton throughout the Gulf. So this is a slide from the spring times, and you can see that the bloom extends from the tip of the Gulf where Eilat is to here, a place called Sharm el-Sheikh. And in the summer, everything is more oligotrophic. And also, it set the stage for the bloom dynamics. So this is, the vertical axis is the chlorophyll concentration during the bloom. And here's the mixing depth during the year, and the R-square is 0.6. And you can plot the same, the R-square goes down to about 0.45, but still highly significant if you plot the mean chlorophyll for the entire year. So it set the stage for the year that follows the winter and the mixing depth that occurred there. Then sometimes, when the mixing is really, really deep, and we published that long ago, you don't see corals in the reef. Everything, in this case, during that year, it's enteromorpha, now they call it ulva. So green alga that smothered the corals. I think that I have, I'll show you the slides later on, and we related to the Pinatubo eruption. So everybody, I think, here knows about the Pinatubo eruption that offset the global warming by maybe 3 years or so. And we didn't get any ash from the Pinatubo, of course. We are, it's about, from the Pinatubo to Eilat, it's about 9,000 kilometers. But certainly the winter was colder, much colder after the Pinatubo, because the major effect of the Pinatubo, and for that matter, any major eruption on the size, on the scale of the Pinatubo, of course, there are not that many eruptions that are on that scale, because that was a gigantic scale. But there are some eruptions that are really good on good scale, and I'll get to that in a moment. But it creates eruption of that. It's not the Iceland eruptions that we had, very coarse, ash that came out. Here we had a quantity in the Pinatubo, 10 to the time of 13 grams of sulfuric acid, if you will, of aerosol. Sulfuric aerosol, and that's the aerosol, and that's taken from a paper by Hupert now, and you can see the aerosol of the Pinatubo a few weeks after the eruption, and that's the normal state of the world as far as that aerosol is concerned, and that, according to that paper by Hupert, and this is based on tree rings and other work on stable isotopes. Whenever we have a major eruption in the tropics, and we have that, that area of the tropic being masked, so the differential heating of the tropics compared to high latitude, which drives the Hadley cells and the wind regime over the globe, is disrupted by the fact that you get less radiation in the tropics. So what happens is that some places on Earth become colder, and some places like North America, the anomaly is warmer after such eruptions. The same in Eurasia, but in the Middle East, it becomes colder by about 3 degrees, and the same in Greenland. Now, if you get 3 degrees colder air during the winter time, and indeed I managed to put my hands on some record that pilots used to record the air temperature before they take off. So I get records that go back to the 50s, and indeed we see at least 2 major eruptions, maybe a third, but look here, this is Beziemini, which was a major eruption, but there was also a cold winter before the eruption. So we have cold winters regardless of volcanism. But whenever you have a major volcanic eruption like the El Quijon in Mexico and the Pinatubo, then the winter temperature is much lower than in other years. Now you get colder temperature, the profile during the winter after the Pinatubo, and the plot that Halpert plotted there was the winter temperature, the anomaly during the winter following the eruption. The eruption occurred in June 91, and that was the cold winter was in 92. And this is the profile of the CTD. That's the one you saw before with the stratification. So we lowered the CTD, we extended a little bit into Egyptian waters, and we lowered the CTD there, and the CTD came back with sediment because that was the bottom depth there. So the mixing, based on models, we think that the mixing reached about 1,000 meters during that time. So you have mixing to 1,000 meters. Imagine the quantity of nutrients that are being entrained and to the surface later, and that's what we see. So both, here, these are the algae, and these are the phytoplankton. So both the phytoplankton, that's the bloom, the spring bloom during the 92 spring, and 3.5 milligram per cubic meter. That's similar to the green water that you find off, California, or Southern California, and we never find these values in the Gulf of Aqaba. It's still pretty blue waters and transparent water. But during that year, that was, we had a submersible, a touristic submersible in the nearby observatory, and they used to take tourists to see the deep reef, the mesophotic reef. They went out of business for 3 months because you couldn't see, beyond 5 meters away because the water was so murky. Anyway, question is, when that bloom, that here you can see a little bit with the light, but you can see more or less the depth of that algal mat. So the algal mat made few changes to the corals. First of all, it masked the light. The corals were exposed for very little light that could penetrate through this thick mat of algae. Secondly, currents stopped. I mean, the corals were not exposed to the currents because of the algae. And thirdly, these algae, they masked the light for themselves in a way. So the bottom layer became anaerobic because there was not much ventilation. So of course, with the and we were not geared up to that. I talked with Mike and Terry. I mean, our lab is out there in the sea. We cannot control it. So here comes the bloom, and we need to do something about it in order to understand it. So we were not geared up to measure everything there. So for example, sulfide we didn't measure, but it's definitely that when we took those algae, went up to the surface, took the mask off and smelled it, I mean, it was very obvious that it was anaerobic in the bottom. So that all these 3 parameters are really damaging corals, and here is, unlike here, we have lots of sea urchins. Sea urchins are major grazers, including also, of course, the fish. So it's hard to see them here, but here in this crevice, under this small knoll of corals, there are 5 sea urchins, and all they needed at that time to eat is that. That was enough. Their functional response is so ineffective. So they didn't graze all the corals because that's the way. I mean, I think that the fish are effective, and we have some indirect, and again, it's not a perfect study by the virtue that we couldn't get all the parameters down, but if you look at the mortality of the coral, so in June, the algae started to recede, the water became warmer, nutrients became lower, but that algae likes the colder water, so it doesn't like very much the warmer water. And what was left behind were about 20% of white skeleton dead corals. So it lasted about 3 months, the corals, so I would say 2 months that they were covered with thick mud, and that killed about 1/5 of the corals along the Gulf. And that's one interesting observation is that the 20% are all branching corals. The massive corals, and I have no explanation, the massive corals are doing much better as far as these three parameters: the light, the flow, and the anaerobic conditions. And that yet to be investigated as resilience to these to that effect by the massive corals. But here we call it nature reserve. That's the control part. And in the nature reserve we have few sections where there are lots of herbivorous fish, mostly acanthurids and sigonids. And they, especially the acanthurids, they have some places where all the group is, the hundreds of fish are staying there. Lynn Montgomery used to work on them, and he documented every day the way they go out and to graze. And usually they pass over a few kilometers on a daily basis to graze for the algae. During that time, they didn't have to swim far. All the algae were there, and they cleared some patches. So there were some patches where we had algae, but they were not, the alga did not develop this map. And this is the control that in those patches that we measured the mortality, there was no mortality of corals. And then we say it's not the colder temperature. Well, it was colder by a few tenths of a degree, but it was not the temperature, it was not the phytoplankton bloom that made the water murky. It was the coverage by that green alga that actually smothered the algae. So then when we were just about to publish that paper, a book came out in, now it's translated, I think also to Hebrew, by Yossi Loya and Rami Klein. And in that book, this is in Hebrew, in that book they have a picture, not as stunning as the one I have, but in Hebrew it says here that the coral reef was covered by green alga, and that caused a substantial mortality, unmeasured, but substantial mortality of the corals in Eilat. And then in small letters, they also say in the winter of 1983. Recall that's the winter after the El Tijon eruption. So what we claim is that and these are the temperatures there, that indeed that winter was colder than normal, so we had some anomaly there. So that disturbance, if we call that disturbance, occurs, well, on intermediate scale. Is that, that when Connell published his paper in Science on the intermediate disturbance hypothesis, he referred to the diversity indices that Yossi Loya got from this reef. And he, in his writing, in that paper in Science, he refers to, well, these are relatively small corals that indicate that some disturbance occurs here on a regular basis, and the diversity, the high diversity of the corals requires that there would be some intermediate disturbance over there, except that we don't have that. We never have cyclones in the Gulf. And we think that this is the intermediate disturbance that clears, and indeed, fifth of the space is cleared, and corals recruited after that. So it may be positive. So on the positive, we have no bleaching. This is really good. And the reef flourishes relatively. On the negative, I'm not sure it's totally negative because it's natural disturbance. But we have coral smothering by algal blooms. And as the say goes, by Jerome K. Jerome in Three Men in a Boat, so there is nothing good without nothing, with something bad into it. So that's his saying, it's not mine, but anyway. So this is the story of the Red Sea and its of the Gulf of Aqaba and its uniqueness. So I'm open here for questions.